Hey everyone, welcome to another deep dive. You know how we love to take a look at all this fascinating stuff. And today we are going to be diving into the world of flight instruments.
Ooh, exciting.
Yeah. So, you're interested in this stuff if you ever look at the cockpit and wonder what are all those dials?
Right?
What are all those gauges?
Yeah.
What is all that information?
Yeah.
How do planes actually stay in the air? And we are
Yeah.
going to be taking a look at a chapter from a pilot training manual
Okay.
to kind of try to figure this out. We're going to talk about different kinds of altitude and airspeed. What happens if your instruments get blocked mid-flight?
Oh, yeah.
So, buckle up and let's get into it.
Yeah. What's so cool is that a lot of these flight instruments
Mm.
are based on
Yeah.
very, very simple principles
Okay.
of physics, but
Yeah.
they're engineered in such a clever way
Yeah.
to be useful in the air.
Okay. So, let's start with one system in particular, which is the
Yeah.
pitot-static system.
Right.
I'm going to guess most people haven't even heard of this before.
I had no.
But it's pretty ingenious. What does it do?
So the pitot-static system uses the pressure of this still air surrounding the aircraft,
Okay.
and it combines that with the pressure created by the plane's movement through the air.
Mm-hmm.
So you get kind of a dual reading there.
Oh, so is it kind of like
I
if
do.
you stick your hand out the window of a moving car?
Exactly.
You feel the air itself, but
Yeah.
you also feel the force of the wind pushing against your hand as the car moves?
Exactly. Yeah.
That's what the pitot tube is doing.
Yep. And it's amazing that this one simple system feeds three very important instruments.
Okay.
The airspeed indicator, the altimeter, and the vertical speed indicator.
Okay, so let's unpack those. Let's start with, I guess the altimeter. That one seems pretty straightforward. I mean, it tells the pilot how high the plane is.
It's not quite that simple
Okay.
because you see the altimeter is essentially a barometer.
Okay.
But instead of measuring the pressure to figure out the weather, it measures the pressure to determine the altitude. The
Yeah.
higher you go, the lower the air pressure.
Makes sense, but hold on. Doesn't air pressure change all the time,
Yeah.
because of weather?
Yeah.
So how does the pilot know that the altimeter is accurate?
That's a great question.
Yeah.
And that's where the whole altimeter setting comes in.
Okay.
So from air traffic control, the pilots get an altimeter setting,
Mm-hmm.
which accounts for the local air pressure at that time.
So it's kind of calibrating it
Exactly. For the condition.
for the current conditions.
Yes.
Gotcha. So there are different types of altitude then.
There's indicated altitude, which is what you read
Okay.
straight from the altimeter. Then there's true altitude,
Mhm.
which is your actual distance above sea level.
Yeah.
And then we've got absolute altitude, pressure altitude, and density altitude.
Whoa.
Yeah.
Okay, so a lot of different types of altitude.
Different ones for different situations.
Yeah.
But here's where it gets interesting. The manual mentions that temperature can also throw off altitude readings.
Okay, so could a pilot think that they're higher?
Yes, than they actually are. That's right. Because colder air is denser than warmer air.
Okay.
So if you're flying from an area of warm air into an area of cold air,
Mm-hmm.
your true altitude might be lower than what the altimeter is showing.
Oh.
Pilots even have a saying about this.
Okay.
Going from high to low, look out below.
Whoa.
Yeah.
That does sound a little unnerving.
It is unnerving,
Yeah, I can see why. That would be important to know.
especially when you're flying near mountains
Right.
or in low visibility.
Right, yeah, exactly. Okay, so that's the altimeter. Let's move on to the airspeed indicator.
Okay.
I mean, that one seems pretty basic, how fast are you going?
Well, again, there's more to it than meets the eye.
Okay.
Like altitude, there are different kinds of airspeed. There's indicated airspeed, calibrated airspeed, true airspeed, and ground speed.
Okay.
And they all take into account different factors.
And there are those color-coded markings on the ASI?
Yes.
What do those mean?
Those are really important visual cues. Think of it like a speedometer,
Okay.
but with some extra information. So you have your white arc, which shows the safe operating range for using flaps. This is important during takeoff and landing.
Gotcha.
Then you have the green arc, which is the normal flight range. Then you have the yellow arc,
Okay.
which is a caution range, only to be flown in smooth air.
Okay.
And then that red line at the top,
Yeah.
that's the never exceed speed.
Oh,
Okay.
yeah. Do not go past that.
Don't go past that.
Okay, so that's 2 out of 3 of the instruments powered by the pitot-static system.
Right.
So the last one is the VSI.
Yes, the VSI.
What is that?
So that's the vertical speed indicator. It tells the pilot how quickly they're climbing or
Right.
descending, and it's measured in feet per minute.
What happens if that gets blocked?
Ooh, that's a good question.
It seems like
That could be dangerous.
it can be. A blocked pitot tube is a serious situation.
Yep.
And it can have different effects depending on where the blockage is.
Okay.
So if only the pitot tube is blocked...
The airspeed indicator will just drop to 0.
Oh, wow.
Not what you want to see.
Yeah, no, that's terrifying.
But it gets trickier because if both the pitot tube and its drain hole are blocked,
oh, God,
the airspeed indicator will actually give you false readings. It will show a higher speed during descent and a lower speed during a climb.
Oh, that's bad.
Yeah, and then if the static port gets blocked, that can cause even more problems.
Okay, like what?
So the airspeed indicator will be inaccurate. The altimeter will freeze, showing the altitude where the blockage occurred, and the VSI will show 0, even if the plane is climbing or descending.
Yikes. So you don't know how fast you're going, you don't know how high you are, and you don't know if you're climbing or descending.
That's a bad time.
That is a very bad time.
Yes.
Okay, so that's why those regular instrument checks are so important. You got to be able to spot this stuff. But so far, we've only talked about analog instruments.
Right.
What about the digital displays you see in more modern planes?
Yeah, those are called electronic flight displays, or EFDs, but they still rely on the pitot-static system.
Okay.
They just process the information differently. Instead of like mechanical gauges, they use an air data computer, or ADC, to calculate and display the information digitally.
What are the advantages of going digital?
Well, reliability is a big one. Plus, they're more compact than all those old school dials and gauges. But maybe most importantly, they can display so much more information.
Like what kind of stuff?
So things like trend vectors.
Yeah, okay. Trend vectors, what are those?
So trend vectors show you where the plane's altitude and speed are heading.
Oh, cool.
Yeah, so it gives you kind of a more comprehensive picture of the plane's current state and how it's changing.
That's really cool.
Yeah, and some EFDs even use an attitude and heading reference system, or AHRS, which uses lasers instead of spinning gyros.
Oh, wow, that's high tech.
It is. It's a big step forward in accuracy and reliability.
So, speaking of gyros,
yes,
let's talk about the next category, which is the gyroscopic instruments. So these rely on some pretty fascinating properties of physics.
Yes, they do.
To provide that essential flight information.
The gyroscopic instruments are based on 2 key principles.
Okay, what are they?
Rigidity in space and precession.
I'm going to need you to break those down.
Okay, so rigidity in space basically means that a spinning gyro wants to stay pointed in the same direction.
Okay.
Even if you try to move its base. Like, think of a spinning top.
Okay.
Like it resists tilting, right?
Right.
Yeah, that's basically what the gyro is doing.
Right, sure.
And then there's precession, which is kind of the tendency for a spinning gyro to tilt at a right angle to the direction of an applied force.
So that one's a little less intuitive.
Yeah, a little counterintuitive.
But it's that characteristic of the gyros that makes them so useful.
Exactly.
Okay, so what instruments rely on gyros?
So we have the turn coordinator, the heading indicator, and the attitude indicator.
Okay, so that's the gyroscopic instruments. But, you know, even with all of these advancements in digital instruments, pilots still rely on one of the oldest tools in aviation, which is the magnetic compass. The
old magnetic compass.
Yeah, like you think it would be. Obsolete by now.
I know.
But it's still super important.
It's incredibly reliable and a vital backup if those other instruments fail.
Okay, so how does it work?
All right, so inside the compass, there's a floating card with magnets. And those magnets align themselves with the Earth's magnetic field. The pilot reads the heading on the card relative to a fixed point called the lubber line.
Okay, but the manual mentioned that reading a magnetic compass can be tricky.
Yes.
Why is that?
So there are a few things that can throw off the compass reading. First, there's variation.
Variation, okay.
That's the difference between magnetic north and true north, which changes depending on where you are on the planet.
So the compass isn't always pointing to true north?
Nope.
Okay.
Pilots have to account for that difference when they're navigating. Then there's deviation, which is caused by the plane's own magnetic field.
Oh, wow. So the plane can interfere with the compass?
It can.
Okay, what else can cause? Right.
We've got dip errors, which happen because the Earth's magnetic field isn't perfectly horizontal.
Okay.
And these errors are especially noticeable. During turns, accelerations, decelerations.
Gotcha.
And all of these factors can combine to create something called oscillation.
Oscillation.
Where the compass needle swings back and forth.
So pilots have to be really careful and understand all these little quirks.
Yeah, they use what's called a compass correction card to adjust for these errors.
Oh, wow.
Yeah.
Okay, so there's a whole other card.
Yeah.
For compass correction.
Yes.
Now, the manual also mentions something called a vertical card, a magnetic compass.
Yeah.
What is that?
So it's another type of magnetic compass.
Yeah.
But it's designed to be easier to read. Instead of like a traditional compass card, it has a rotating dial with a miniature airplane on it that shows the heading.
Oh, cool.
Yeah.
Okay, so that one's...
It's less prone to some of those errors.
Yeah.
Especially dip errors. However, it still has its limitations.
Okay.
Particularly when the plane is turning.
So it seems like each type of compass has its pros and cons.
That's right.
Gotcha. And pilots need to know both.
Exactly.
Before we wrap up this section, let's quickly touch on one more instrument, which is the outside air temperature gauge.
Right.
Or OAT gauge. It seems pretty basic. Why is it so important?
You know, it might seem simple, but knowing the outside air temperature is crucial for calculating things like density altitude, which affects how the aircraft performs.
Sure.
So the OAT gauge uses a bimetallic strip that twists and untwists as the temperature changes to give you a reading of the outside air temperature.
So even knowing like something as basic as the temperature can have a huge impact.
It can on how the plane flies.
It's amazing how all this stuff works together to keep a plane in the air.
It really is.
I mean, each instrument plays such a vital role in giving the pilot the information they need to make safe decisions. Okay, so that was a great overview of those kind of, I don't know, core instruments, I guess you could say. The pitot-static system, the gyroscopic instruments, and the different types of compasses.
Right.
It's fascinating to learn how this stuff actually works and how they provide pilots with that critical information they need to fly safely. But what happens when things go wrong?
Ooh.
What if these instruments malfunction in flight?
That's a great question. And that's something that pilots are actually trained to handle.
Okay.
So in the next part of our deep dive, we're going to explore some of those scenarios.
Yeah.
And we're going to discuss how pilots can troubleshoot instrument issues. Yeah. And maintain control of the aircraft even in those challenging situations.
Okay, so things are going to get pretty interesting.
I think so. Welcome back.
All right, so
let's dive into some real-world scenarios and see how these instruments actually work in action. Imagine a pilot is cruising along, and suddenly the airspeed indicator starts acting up, giving erratic readings.
I can already feel like my palms getting sweaty just thinking about that. So what would be the first thing a pilot would do?
The most important thing is to stay calm and assess the situation.
Right.
Panicking is not going to help anyone. So they would start by checking for any obvious signs of blockage in the pitot-static system. Things like ice buildup or debris can cause problems.
So like a visual check of the instruments.
Exactly. But if there's no visible blockage, then the pilot needs to figure out, is it a problem with the pitot system or the static system?
How do they figure that out, like in the air?
That's where their knowledge of the systems comes in. They would cross-reference with other instruments. For example, if the altimeter is also acting strangely, that probably points to a problem with the static system. But if the altimeter is steady and the airspeed indicator is jumping around, it's more likely an issue with the pitot system.
So it's like a puzzle. Like using one instrument to give you clues about another one.
That's a great way to put it. Pilots need to understand how all these systems are interconnected.
Okay, so let's say the pilot determines it's a pitot system problem.
Okay.
What do they do? I mean, if the airspeed indicator is unreliable, that seems like a pretty big deal. How can they fly safely without knowing their speed?
It's definitely not ideal. But pilots train for these situations. So they would rely on other cues to maintain safe flight.
Like what?
Things like the pitch attitude of the plane, the sound of the engine, and their overall feel for how the aircraft is performing.
So almost like flying by feel.
You could say that.
Right.
But it's not just intuition.
Right.
These pilots have a deep understanding of their aircraft, and they are trained to recognize and interpret those subtle signs.
That's incredible. Okay, what about a problem with the static system then?
All right, so if it's a blocked static port, the pilot might try using the alternate static source if the aircraft is equipped with one. This basically introduces static pressure from inside the cockpit into the system.
Is that a perfect fix?
Not quite. The alternate static source can cause slight errors in the instrument readings.
Okay.
But it is a valuable backup in an emergency.
So it seems like knowing how to troubleshoot these problems is just as important as knowing how the instruments work.
Absolutely. And that's why pilot training involves so much practice in simulators where they can safely experience and react to all these different instrument malfunctions.
So they throw all kinds of stuff at them in the simulator.
Yeah, all kinds of crazy scenarios.
Okay, so let's talk about what happens if a gyroscopic instrument acts up.
Okay.
What if, like, the vacuum system fails?
Okay.
And the attitude indicator or heading indicator stops working?
A vacuum system failure is a serious situation.
Okay.
Because without a working attitude indicator, it can be extremely difficult to maintain control of the aircraft, especially when flying in instrument meteorological conditions, or IMC.
Yeah.
Where you can't see outside.
Right, so you're essentially flying blindfolded.
Kind of, yeah.
Yeah.
Losing that visual reference to the horizon can be very disorienting.
Wow. Okay. So what can the pilot do if that happens?
Well, the first thing they would do is check if there's a backup vacuum system.
Okay.
And try to switch to that. If not, they have to rely on other instruments, like the turn coordinator and the magnetic compass, to try to maintain their orientation.
But we talked earlier about how those instruments have their own limitations. The turn coordinator doesn't tell you the bank angle, and the magnetic compass can be affected by all those errors.
That's right. So in this situation, the pilot's training and experience become even more critical.
Okay.
They need to carefully interpret the information they're getting from the remaining instruments and make really informed decisions.
So it really highlights the importance of being able to adapt and think on your feet.
Exactly.
In those high-pressure situations.
It also emphasizes the importance of regular aircraft maintenance and thorough pre-flight checks.
Yeah.
Making sure all the instruments are functioning properly can prevent a lot of these problems from even happening.
Okay, speaking of the magnetic compass, we mentioned earlier that it can be tricky to use, especially during turns.
Yes.
Why is that?
Well, it all goes back to those dip errors.
Okay.
When the aircraft is turning, the compass card tilts, and this can cause the reading to lead or lag the actual heading.
So if a pilot relies solely on the magnetic compass during a turn, they could end up off course.
That's right. That's why pilots use a combination of instruments and techniques to make accurate turns.
What are some of those techniques?
Well, one technique is called timing the turn.
Okay.
Instead of fixating on the compass heading, the pilot uses a clock to estimate how long it takes to turn a certain number of degrees.
So they're incorporating time into their navigation.
Exactly. They might also use visual cues,
okay,
like the position of the sun or the horizon if they're visible, to help them maintain their orientation.
It seems like flying, especially in instrument conditions, involves constantly like cross-checking information and making adjustments based on multiple sources of data.
It's a mental juggling act.
Yeah.
Pilots have to be constantly aware of their situation and making decisions based on the best information available.
So that brings us to, I guess, a potentially even more challenging scenario.
Uh-oh.
What happens if multiple instruments fail at the same time?
It's a rare occurrence.
Okay.
But it is something that pilots train for extensively in simulators. They learn to rely on their knowledge, their skills, their judgment to maintain control of the aircraft.
So what are some of the strategies they might use?
Well, the first step is to try and identify the root cause of the problem.
Okay.
Is it a vacuum system failure? A blocked pitot-static system? Electrical issues? Once they have a better understanding of the problem, they can start troubleshooting and potentially restart or reset affected systems.
So it becomes like a real test of their problem-solving abilities.
Absolutely. They have to think outside the box.
Yeah.
Use all the resources available to them.
And communication is key.
Absolutely.
In that situation, right?
They would immediately contact air traffic control, explain the situation, and request assistance.
So they're not totally alone.
Exactly. They have a whole team of professionals on the ground supporting them, providing guidance, and helping them navigate safely.
That's reassuring. Okay, so we've talked a lot about dealing with instrument malfunctions, but what can pilots do to prevent these problems from happening in the first place?
Well, regular maintenance is paramount.
Okay.
Pilots need to ensure their aircraft undergoes routine inspections and that all the instruments are calibrated and functioning properly.
So well-maintained plane is a safer plane.
Absolutely. And pre-flight checks are equally important. Before every flight, pilots meticulously inspect their aircrafts, paying close attention to the pitot-static system, the vacuum system, and all the instruments.
So basically looking for any signs of wear and tear?
Yes. blockages damage. They're also checking for proper instrument readings.
Yeah.
And making sure everything is working as it should.
Attention to detail is key.
It is an essential part of being a pilot. And it's not just the pilot's responsibility. Mechanics play a vital role in ensuring aircraft safety as well. They perform detailed inspections, repairs, and preventative maintenance to keep those aircraft in tip-top condition.
So it's a team effort.
It is.
Everyone from the mechanics to the pilots is playing a part in ensuring safe and reliable air travel.
That's right. It's a complex system with many moving parts, but it all works together to get us safely from point A to point B.
Well, this has been a fascinating look at all the challenges that pilots face when dealing with these instrument malfunctions. But, you know, technology is constantly evolving.
It is. There are some incredible advanced instruments out there that are pushing the boundaries of what's possible in aviation.
So what are some of those cutting-edge tools, and how are they changing the way we fly?
That's a great question, and that's what we're going to explore in the final part of our deep dive.
Okay.
We'll delve into the world of advanced navigation systems, weather radar, and all those other high-tech instruments that are making flying safer, more efficient, and more accessible than ever before.
Okay, sounds like we have a lot more to uncover.
We do.
So we'll be right back after a short break to continue our journey into the world of flight instruments. Welcome back to our deep dive on flight instruments. We've talked about so much already, but now it's time to explore the cutting edge. Like, what are some of the tools that pilots use when things get really tricky, like in bad weather or low visibility?
So one instrument that comes to mind is the VOR.
VOR?
Yeah, or VHF omnidirectional range.
Yeah.
It's a ground-based navigation system that transmits radio signals.
Okay.
And pilots use a VOR receiver in the cockpit to figure out their direction relative to the VOR station.
So it's like a network of radio beacons across the country that guide pilots.
You got it.
Okay.
VORs are strategically placed, so pilots can navigate precisely, even when they can't see very far.
Gotcha.
It's a fundamental skill for instrument pilots.
Okay, so what about landing in bad weather? Are there instruments that help with that?
Absolutely. One of the most important is the ILS, or Instrument Landing System. This is another ground-based system. But this one provides very precise guidance.
Okay.
During the approach and landing, imagine two beams, one horizontal, one vertical, that the plane can follow down to the runway.
Oh, wow. So the pilot uses, like, the ILS receiver to line up with those beams and basically write it down to a safe landing.
That's the idea.
That's really cool.
It's especially crucial when visibility is low and landing can be dangerous. The ILS lets pilots land safely and efficiently, even when they can't see the runway, until the very last moment.
That is wild. It's amazing that that technology exists.
I know. It's pretty incredible.
Yeah. Are there any other tools that help make safe landings?
There are. So, for example, radar altimeters measure altitude above the ground, not sea level, which is very helpful when you're close to the ground.
Gotcha.
And then we have ground proximity warning systems, or GPWS, which warn pilots if they are getting dangerously close to the terrain.
So it seems like there are multiple layers of safety built into the system.
Right. Redundancy is key in aviation.
Which makes sense when you're talking about flying.
Absolutely.
Okay, so we talked about navigating in low visibility, landing in bad weather. What about avoiding, like, hazards in flight?
Okay.
Like storms?
That's where weather radar comes in, another game changer. In aviation safety, this system detects precipitation and displays it on a screen in the cockpit.
Oh, wow.
So pilots can actually see areas of heavy rain, thunderstorms, or any other hazardous weather they need to avoid.
So they can see the storms forming and, like, plan their route around them?
Yes.
That's amazing.
It really is.
Okay. And that's not even the only tool.
No. For avoiding hazards, we also have TCS.
TCS.
Or traffic collision avoidance systems.
So that's like air traffic control in the cockpit.
Exactly.
Helping pilots avoid other planes.
It gives pilots an extra set of eyes in the sky.
That's great. Okay, so it sounds like all of these systems work together
They do.
to make flying safer and more efficient. But what does the future hold?
The future is bright for aviation technology. Advancements in computing and sensor technology are leading to even more accurate, reliable, and sophisticated instruments, all to enhance safety, efficiency, and ultimately make flying more accessible to more people.
That's exciting.
It is.
Well, this has been such a fascinating deep dive. I feel like we've covered so much, from those basic principles that make these instruments work to these high-tech systems that are shaping the future of aviation. It's incredible to think about all that goes into making flight possible. It really is. Every time you board a plane, you are trusting this complex system of instruments and the skilled professionals that operate them.
Yeah, exactly.
And that's pretty amazing.
It is.
Well, thanks for joining us on this deep dive into the world of flight instruments. Until next time, fly safe.